This video is for the revision of chemical energetics. Heat is a form of energy, and this energy can be transferred between the system and the surroundings. So if we have a beaker, a cup, and a thermometer, if a reaction happens in here, let's say there's some water as well. So if a reaction happens here and the temperature of this water increased, it means that the temperature of the surrounding increased, and that would mean the system lost energy. So that would mean an exothermic reaction. So the reactants has more energy and the products have less energy, and the energy change is negative. This is for an exothermic reaction. Similarly, the opposite now. So if the temperature in here decrease, it means that the system has absorbed the energy, so the reactants has less energy and the products have more energy, so we'll get enthalpy change that is positive here, and that would mean it is endothermic, and this is the activation energy. Before learning this chapter, we do need to remember the normal states or the standard states for some of the reactants, some substance that is commonly used in IBDP questions. So for example, if I have Cl, I have to remember that Cl comes in Cl2 gas, Br is in Br2 liquid, and would be N2 in gas. So these are common elements. So some of these occur naturally in diatoms, and they're in gaseous states. And for carbon, it's graphite, so it's a solid, and metals are in solid. I2 is also in solid. Br2 is in liquid. When you're studying the standard enthalpy change of combustion, study the definition and be sure to understand how to write the equation with respect to the definition that you remembered. So enthalpy change when 1 mole of a substance is completely burned in oxygen, meaning the oxygen has to be in excess. So for example, if I have graphite, I need enough oxygen to form something that is standard. So make sure that the thing you want to combust must be 1 mole. So other examples is I have carbon monoxide here and I have hydrogen gas here. So make sure that all these that you want to combust is 1 mole, that's 1 mole of it, and make sure the oxygen is in excess, so there's enough of it to form these that are in standard conditions. So meaning if graphite was combusted with not enough of oxygen, it's going to form CO, carbon monoxide in gas. So that's not standard. So that won't fit the definition of standard enthalpy change of combustion. Next, let's look at standard enthalpy change of formation. So standard enthalpy change of formation, it says that it's the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. So these elements has to be standard, and this has to be 1 mole. So if we look at the equation graphite plus oxygen, you get carbon dioxide. It appears both in standard enthalpy change of combustion and formation. They look the same. Why so? Because for combustion, this has to be 1 mole and this has to be standard, so it fits. And for standard enthalpy change of formation, these has to be elements and this has to be 1 mole. So it fits as well. So since it fits in both, it is the standard enthalpy change of combustion of graphite, and it's also the standard enthalpy change of formation of carbon dioxide. Let's look at another example. Okay, so H2 plus half oxygen, I get H2O in liquid. So I do have 1 mole of the H2O liquid, and these are the elements. So it fits the standard enthalpy change of formation. And I did combust hydrogen, and get H2O in its standard form. So it is also standard enthalpy change of combustion. So it fits in both. But what about the next one? I have H2 here and O2 here. So these are still the elements, so it fits. And I have H2O in gas, but enthalpy change of formation, it just says that these needs to be 1 mole of the thing you want to form. And these has to be the elements under standard conditions. So for forming to form a H2O gas, it's only standard enthalpy change of formation of H2O gas, but it won't be standard enthalpy change of combustion of H2 because the H2O would not be in standard conditions. H2O in standard conditions would be in liquid. So therefore, the last equation only fits for formation and not for combustion. So I put the label here, combustion, this needs to be 1 mole. And for formation, this needs to be 1 mole. For combustion, this needs to be in excess. Oxygen needs to be in excess. And the products needs to be in standard. And for formation, the reactants need to be in elements or standard. And let me give you a second to figure out, is this standard enthalpy change of combustion, formation, or both, or neither? Okay, let's figure this out together. So I have a mole of graphite here. I don't have enough oxygen to form standard products. So then it won't be standard enthalpy change of combustion because the oxygen is not enough to form standard compound of carbon and oxygen. The standard compound for carbon and oxygen would be carbon dioxide. So this is not standard enthalpy change of combustion, but can it be formation if I want to form a mole of carbon monoxide instead? Are these elements under standard conditions? Yes, they are. So this is standard enthalpy change of formation of carbon monoxide, but not standard enthalpy change of combustion for graphite. Next, standard enthalpy change of neutralisation says that it's the enthalpy change where 1 mole of water is formed in the neutralization between acid and alkali. And this must be carried out in aqueous solutions under standard conditions. So for example, if I have HClAq and NaOH AQ, I'm gonna get NaClAq plus 1 mole of water in liquid. So it has to be 1 mole of water. Okay, other examples. Okay, let's look at these two equations. Sulfuric acid with sodium hydroxide, we get sodium sulfate with water. So this equation, the second one, it doesn't fit the description here, the definition here, when it says 1 mole of water must be formed. So there's 2 moles of water here. So this is actually 2 times standard enthalpy change of neutralization. So this is standard enthalpy change of neutralization because 1 mole of water is formed. So it's not dependent on the acid or the base. It doesn't have to be 1 mole of acid nor 1 mole of base. We focus on the water that is formed. It has to be 1 mole. Okay, next part is Hess Law. Hess Law says that the total enthalpy change of a reaction is not dependent on the route taken. So no matter what route we take, as long as we start from the same place and ended up at the same place, it doesn't matter if we use this route or this route or this route, but we did start from here and ended here. They all are the same. So if we look at this enthalpy change here, H1 is when we go direct. And 2 is if we break everything here, break all the bonds here, whether it's single, double, all the bonds we break here, and we break all the bonds here. So it's a long way to take, but it will still give us the same value. So what it means here is that if we have H1 here, it's equal to taking H2 and the reverse of H3. So that's what Hess Law means. The rule is that this and this must have the same initial point. And also this and this must have the same final point. Let's calculate this enthalpy change, and I'm going to display it so that we can see the bonds. Okay, so the reason I display all this to show every bond is so that I can double check that all my carbons have 4 bonds, my oxygen should have 2 bonds, my nitrogen should have 3 bonds, and H should have 1 bond when they have no charge. So that will help me double check that all the bonds are correct, because a single bond and a double bond makes a difference in its bond energy. Let's check for what has not been broken. So I can see that this portion was not broken nor formed because it's still here. Okay, the other thing that was not broken was this, because it's still here. So I do not need to break those. So I'll need to break a CO here, a C double bond O, and a C single bond H. I need to form a new C single bond C, C single bond O, and an OH here. Let's get that from the data booklet. So we need the C double bond O. We need a C single bond O. We need a C single bond C. We need OH. And the C single bond H. So I put the values here. Let's calculate the bonds broken, and we'll calculate the bonds formed. Please write that separately in exams because they give you error carry forward marks. So this is what I've got. So write them separately, the bonds broken and bonds formed. 1218 in positive value and 1167 in a negative value, and I got positive 51. Just a reminder here, double bonds are stronger and single bonds are slightly weaker than a double bond. And for OO, so O to another O in single bond is 144. O to O in a double bond is much stronger, 498. And in ozone, it's a 1.5 bond. So it's somewhere between, the strength is somewhere between a single bond and a double bond. So here, single bond, double bond, and a 1.5 bond, which is somewhere in between these two figures. Keep in mind that the data booklet might vary. So sometimes if you use a different data booklet, you might get a variation in the answers. So just refer to the data booklet for your sitting of exam. You can also form a Hess Law cycle if you're given the enthalpy change of formation of some substances here, or if you're given the standard enthalpy change of combustion of those substances. You keep in mind that standard enthalpy change of combustion is also given in the data booklet. So if you don't see the values in your question paper, it means that you have to look for it in the data booklet. And the values might vary a little bit for different data booklets. Okay, the first question, they give us the standard enthalpy change of formation of all these substances. So we know that the definition of standard enthalpy change of formation, it needs to form 1 mole of something, and it must start from their elements. So from elements to a mole of something, from elements to a mole of something. Okay, from elements to 2 mole of this. So that's 2 times the enthalpy change of formation. And elements to a mole of this. Okay, what are the elements? In fact, in the cycle, I don't really need to write the elements here. So I just put the word element there just now. So the elements are, for example, calcium must be in solid. So that's a metal. And we know that F2 is in gas, and so on. Next, I'll write all the values given here. So I put the values there. And since we're calculating this, so it doesn't matter if I use this short way or if I go the long way. So now I'm using the long way. And the long way shows that I need to go down. So it's the opposite of enthalpy change of formation. So I'm going to put that as positive 1220. On this side is also the wrong way. So also positive 814. So what I want to remind you is that these are the initial materials and this is where we end. So we're going from this bubble to the other side in the same, in the other bubble. Okay, but these arrows are in the correct direction. So I'm just gonna add that 2 times negative 271 plus negative 1434. So I do not turn the arrow around for this. So this is my answer. And for a shortcut, if it's a very direct question, then you can do this. Just take the products going the right direction and minus the reactants, which is the wrong direction. Okay, so I'll show a separate working for this. So total up all the products, enthalpy change of formation of the products, and minus the enthalpy change of formation of the reactants. And I'm going to get the same answer here. Next question is how to use the enthalpy change of combustion to calculate the enthalpy change of a reaction. So it says here, calculate the enthalpy change of formation of methane. So we do need to know how to write the enthalpy change of formation of methane. We need to know the elements. They are graphite and hydrogen gas. And since there's 4 here, I'll need 2 moles to get methane. Okay, they gave me the standard enthalpy change of combustion of each of that, methane, graphite, and hydrogen. So what is going to be formed when they are combusted? When they're combusted, it will form carbon dioxide and water. So graphite, when it's combusted, it's going to form carbon dioxide, 2 moles of hydrogen, so that's 2 of enthalpy change of combustion of hydrogen gas that will form water. And as for methane, if you combust it, it's going to form carbon dioxide and water. So I'm going to put the values in like what I did just now. Okay, remember that we're combusting hydrogen twice because there's 2 moles here. So we need to multiply by 2. So we're going from these reactants to form this product. No matter what route we choose, it's going to be the same. We're actually calculating this. And we're going this way. So the reactants, they're in the correct direction, but the product, we need to turn this arrow around. So reactants in the correct direction, reactant in the correct direction, and products, turn around the arrow, so minus here, and I'm gonna get negative 74.8 kilojoules per mole. So in other words, I can say that I total up the standard enthalpy change of combustion of the reactants and minus the total of the standard enthalpy change of combustion of the products. So this is also useful. Next, we're going to calculate the enthalpy change by the results of experiment in the lab. Okay, so there's 100 centimeter cube of acid and same thing for base. They have the same volume and concentration. Volume and concentration is the same. And the temperature rise is 3.4 degrees Celsius. So if they give us the temperature rise, that will be the same thing as Kelvin. We also need the density to know the mass of the solution in here. So we're going to use this formula. And the mass here is the mass of the solution in here. So in this case, 100 plus 100, that's 200 centimeter cubes, which means 200 grams. C is given here. Usually you will just get the value from the data booklet. So just follow the one from your data booklet. And they already give the change here. So if they didn't give the change, you'll have to take the final minus the initial to know what's the change. Okay, to know the number of moles, this mole has to be the mole of water since we are calculating the enthalpy change of neutralization here. So not the acid, not the base, but the number of moles of water formed. I'm going to write the equation down here and calculate what's my mole of water. So this is a very simplified question. It's 1:1:1 and 1:1. So usually you do need to find out what is the limiting reagent. That will be the one that affects the product of the water. So now we know the mole of the water is 0.05. Now this is going to give my answer in joule per mole. So I need it to be in kilojoule per mole. So I'm going to put 1000 here to change it to kilo. So my answer is 56.8. And since we know that there's a temperature rise, so it's exothermic, so negative 56.8 kilojoules per mole. Now, if your question is something like this, and it's to calculate the standard enthalpy change of combustion of a certain alcohol in here, then your M would be the M here, the solution or the water here that has been heated up. And the mole is per mole of what has been combusted. So it's per mole of the alcohol down here.